Alkynes can also undergo addition reactions. The reaction of an alkyne with one equivalent of hydrogen bromide generates a vinylic bromide. Note that the yield of this reaction is quite low. The reaction follows the same mechanism as the addition reaction for alkenes, with the proton adding to generate the most stable possible intermediate cation, followed by the addition of the nucleophilic bromide. The low yield is due to the relatively high energy intermediate cation. Carbocations we have studied before have the positive charge in a vacant p orbital. A vinylic cation, formed by protonation of an alkyne, has a positive charge in an sp2 hybrid orbital, which lies much closer to the nucleus, destabilizing the cation. If excess hydrogen bromide is reacted with an alkyne, a geminal dibromide is produced in high yield. This reaction proceeds through the same intermediates to produce an initial vinylic bromide. The intermediate vinylic bromide can then be protonated to generate a resonance stabilized cation, which then reacts with bromide to give the final product. The stabilities of the resonance stabilized cation and the final product drive the reaction to completion, allowing a high yield of the final product. Alkynes also undergo acid-catalyzed hydration. However, the product of the reaction is not an alcohol. Instead, a carbonyl compound, typically a ketone, is the observed product. The reaction mechanism for alkyne hydration is initially identical to that for alkene hydration. Protonation of the alkyne generates a relatively unstable vinyl cation, which then reacts with water, acting as a nucleophile. The product of this reaction is an enol. Under acidic conditions, enols rapidly tautomerize to ketones. The yield of the reaction remains low, however, due to the instability of the intermediate vinyl cation. Unlike the reaction of alkynes with one equivalent of hydrogen halide, the hydration of alkynes can be synthetically useful, provided a stronger acid or mercury 2 salts are used as catalysts. These catalysts allow the hydration to proceed with high yields. Conjugated dienes, such as 1,3-butadiene, also undergo electrophilic addition reactions. The addition frequently leads to a mixture of two isomers. The product with the new hydrogen and the chloride on adjacent carbon atoms is referred to as the 1,2 addition product. This product is what would be expected if the hydrogen chloride added across one of the two pi bonds. However, a second product is also formed where the new hydrogen and the chloride are separated by 4 carbon atoms. This product is called the 1,4 addition product. Note that in this product, the pi bond is in a different location from either of the pi bonds in the starting material. The mechanism of the addition to the 1,3-diene has the same first step as the addition to an isolated double bond. The proton is added across one of the pi bonds to generate the most stable carbocation. The presence of the second pi bond makes this an allylic cation with 2 resonance contributors. There is a partial positive charge on 2 carbon atoms in this cation. The addition of chloride to each of the sites generates the 2 observed products. If hydrogen chloride is reacted with 1,3-butadiene at room temperature, 1-chloro-2-butene, the product of 1,4 addition, is the major product. If the same reaction is conducted at minus 80 degrees Celsius, 3-chloro-1-butene, the 1,2 addition product, becomes the major product. This is an example of a reaction that can generate a different major product depending on whether it is under thermodynamic or kinetic control. A reaction under thermodynamic control possesses enough thermal energy to undergo an equilibrium between starting materials and products. The reaction is reversible. Conversely, if there is not enough thermal energy available to allow the reverse reaction to proceed, the reaction is irreversible and is said to be under kinetic control. After the protonation of the diene and formation of the allylic cation, at low temperature, the subsequent addition of the chloride anion occurs irreversibly. Because of its higher degree of substitution, there is a greater concentration of positive charge at the 2 position of the cation. In addition, after the cleavage of the hydrogen-chlorine bond, the chloride anion is in close proximity to this carbon. As a result, this will be the first carbon to bond with the chloride anion to form the 1,2 product, called the kinetic product because it is formed first. At higher temperatures, the reaction of the allylic cation with the chloride anion becomes reversible, and the chloride anion reacts at both the 2 and 4 position of the cation in an equilibrium reaction. The product of the addition of chloride to the 4 position is a disubstituted alkene, which is a more stable product than the monosubstituted alkene formed by addition to the 2 position. Under the equilibrium conditions, the most stable product predominates. The more stable 1,4 product is called the thermodynamic product. Terpenes are biochemicals which contain a carbon skeleton comprised of linked isoprene units. Terpenes were briefly discussed earlier in the semester in our review of lipids. Terpenes are not directly biosynthesized from isoprene, the common name for 2-methyl-1-butene. Instead, 3 molecules of acetic acid are trimerized to form 3,5-dihydroxy 3-methylpentanoic acid, commonly called mevalonic acid. Decarboxylation and dehydration of mevalonic acid, plus the formation of a phosphate ester with the remaining hydroxyl group, gives isopentenyl pyrophosphate, which contains the basic isoprene unit. Isopentenyl pyrophosphate is enzymatically protonated and then deprotonated to generate dimethylallyl pyrophosphate. This leads to a more stable double bond in the biomolecule. Dimethylallyl pyrophosphate loses the very good pyrophosphate leaving group to form a resonance stabilized carbocation. This cation can then react with another molecule of isopentenyl pyrophosphate to form a dimeric tertiary cation. Enzymatic deprotonation of this cation leads to isomeric geranyl pyrophosphate and neryl pyrophosphate. Both of these compounds can lead to a variety of terpenes. Neryl pyrophosphate is also the precursor for cholesterol and other steroids. In summary, strong Bronsted acids add across double and triple bonds in a process called electrophilic addition. This is a multi-step process. The first step is the addition of a proton to form a carbocation. Not every system with pi bonds readily undergoes electrophilic addition. Benzene is particularly unreactive. The addition of a Bronsted acid across an unsymmetrical double bond or triple bond is regioselective. This regioselectivity is referred to as Markovnikov's rule, where the proton typically adds to the least substituted carbon to form the more stable cation. These cationic intermediates can undergo rearrangement to a more stable cation if such is available. When water adds across a pi bond, the reaction is called hydration. This reaction typically requires an acid catalyst to proceed. The addition of a Bronsted acid across a triple bond leads to a vinyl substituted alkene. Due to the instability of the intermediate vinyl cation, this reaction typically proceeds in low yield. Acid-catalyzed hydration of an alkyne leads to an enol. This type of alcohol rapidly tautomerizes to the more stable isomeric ketone. A conjugated diene undergoes electrophilic addition via competing 1,2 and 1,4 addition mechanisms, producing a mixture of products. 1,2 addition predominates at lower temperatures when the reaction is under kinetic control. Under higher temperatures, thermodynamic control is more likely, and 1,4 addition will produce the major product.